They are asking for a schedule, detailed schedule when the load varies from a minimum to maximum value. So far we have come across so shown on the board is the problem. So far we have discussed problems of this type. That there are two cost characteristics which have been given for you, and the load is mentioned for you like 200 megawatts, and you are solving this problem in order to get an economic generation. So how we have solved this problem? We consider ELD without losses. We do have two conditions. The first condition is the sum which gives us there are two plants P1 plus P2 that is equal to 200. Second condition is IC must be constant, which means IC1 here I do have two plants. IC1 is equal to IC2, which is so solving these 1 and 2. Solving this 1 and 2, I'm getting so these are the two generations, P1 and P2. If I have considered ELD without losses, given my load is 200 megawatts. So we are using two conditions. One is sum of all the generations must be equal to your demand. The second one is incremental cost must be equal. Now we will move on to another load. Now you see the sum, I have taken a different load, 250 megawatts. The first condition remains the same. Sorry. In the first condition, this will become 250 because the sum of generations must be equal to your demand, which is 250. First condition has varied. Second condition remains the same. Again, you need to solve all these two equations. Again, you are supposed to go with P1 and P. Like this, for every change of demand, you are supposed to compute all the things again. You are supposed to get back to the generation cycle. Now, let us suppose this is the problem. They are saying that the load is varying from 50 megawatts to 500 megawatts, and they want the generation of the two plants when the load is varying from 50 to 500 megawatts. So this is the problem. Now let's solve this problem. It doesn't mean that we have to take each and every value of the load 50, 51, 52, not like that. We'll just plot a graph, and from that graph, we will determine what are the economic generations at different times. So I hope you are having a calci. How many of you do have a calci? Can anyone raise your hand? Thank you, then. Now let's get back to the problem. See, I do have two costs. Now, C1 and C. I'm supposed to go with again ELD without losses. So step number one, ELD without losses. IC1 must be equal to IC, isn't it? And it must be some constant, and I will take that as some lambda. So what is IC1 here? 0.04 P1 plus 2. This is 0.08 P2 plus 3. That is equal to some lambda. Now what I will do here, see, P1 in terms of lambda, I will be writing down here. Right. These are my equations P1 and P2, where lambda is some random constant. I don't bother about that constant. I will take it as some random constant. So P1 and P2 both are written in terms of lambda. Now, if possible, I will try to solve this equation, or else you can leave them like that only. Now, 1 minute. Yeah. Now see here. Now I'm gonna draw a table now. Lambda, P1, P2, and sigma P. Now this is my table now. Now if you table is see, I choose some random value of lambda as 0. I'll take random value of lambda as 0. If lambda is equal to 0, then what is P1? P1 we will get somewhere as negative value, isn't it? What is the value? Minus 2 by 0.04, isn't it? So it is going to be minus 2 by 0.04. Approximately. It will be some negative value. What is that value?
Minus 50.
Right. What about this one?
Minus 37.5.
Since the generations cannot be negative, I'll round this one as 0 and 0, and I will mark as 0. This is my total generation as of now. Now I will slowly increase my value as 1. It is your choice, but I'm slowly increasing it as 1. So 1. What is the value? 1 minus 2 is minus 1 by 0.04. That is going to be minus 20. Here, 1 minus 3 is minus 2 by 0.08. Again, it is going to be minus 25. Again, I will round it up. 0, 0. Now I will go back to 2. For 2, this is going to be a perfect 0. This is going to be minus 12.5. So again, this will be rounded up 0. Again, I will go back to 3. This will be, how much it will be? Plus 25. This will be a perfect 0. So my total generation is 24. 4. This is going to be 15. This is going to be 12.5. 37.5. Next 5. This is 75. This is 25. And my generation is going to be 100. Am I correct here? Anybody calculating?
Yes, sir.
Linear equations కాబట్టి increment ఎంత ఉంటుందో దాని ప్రకారం రాసుకుంటూ వెళ్ళిపోతున్నాను. Next I go with 6. This will be 100. This will be 37.5 and it will be 137.5. See, these are linear proportions. Now I'm like this, I will directly go to a larger set at 10. Let us at 10, what is the value? 10 minus 2 is 8. 8 by 0.04. It is going to be
200. 200.
200. And what is this value?
$87.5.
Sure.
Yes, sir.
So 287.5. Now I'll go with 15. I'm slowly increasing my steps. If it is 15, what is going to be value? $325. Sure. Something like that.
Yes, sir.
Yes, sir.
Right.
So 325. Now what about this one?
150.
150. So the final value is going to be 475. 475. Now 475 I was saying, I'll go with 20. If you want, you can decrease the value, but I'm going back to 20 itself. It's going to be 450. It's going to be 222.5, I think. It's going to be 672.5. So this is the calculations which we are doing without knowing the demand value. We have not chosen any demand value. We are just randomly taking lambda. Lambda is the incremental. Isn't it? This is some random concept. This is the incremental cost. We are choosing it randomly and we are computing P1 and P2. And remember, these two are going to be the linear curves as mentioned earlier. ICs are linear curves. So slowly I am calculating all these things, calculating the entire generation. Since there is no demand, since there are no losses, my total generation is equal to the demand. Now I am going to draw a graph. I will arrange these things. Now this is the demand, and these are P1 and P2. Carefully, P1, P2, IC, whatever you want, you can draw it here. If the demand is 0, both my generations are going to be 0. So first of all, I will draw the graph of P1 versus P demand. P1 versus P demand. See, 0, 0, 0, 0. At 25, its value is going to be 25. At 37.5, its value is going to be. Am I right now? Am I right? Right. At 62.5. Yeah. At 62.5, it is going to be 50. Next at 100, it is going to be 75. Next at 137.5. Okay. At 137.5, it is going to be 100. And at 297.5, it is going to be 200. This is my curve of PD with respect to P1. Similarly, if I draw with P2 with respect to PD, now 25 also, its value is 0. 62.5, its value is going to be 12.5. For 100, it is going to be 25. 287, it is going to be 7. So this is P1 curve. This is going to be P2 curve. This is going to be P1 and P2 curves. Now let us suppose if my demand is somewhere around 170, I can directly draw a line here. This is 170 line. So this is my P1 and this is my P2. Understood now? So just after drawing the curves here, I can directly find out what is the generation for some given demand. The only thing is that I struggle a lot to draw these curves. Initially, I have to make a lot of calculations and I need to draw it. But with the modern computers, it is very easy. Then just a plot for infinite values. So draw a plot and just find out what is your demand and just note down what are the P1. Got it? These are called as generation schedules, economic generation schedules. Now let us suppose, have you understood how to draw these things? Just only picking up a random value and going on finding out P1 and P2 and then computing the total generation and next drawing the graphs. From these graphs, we will be picking out the individual generation for a given demand. Earlier case, we had a fixed demand. Now they say that the demand is increasing. So we have tried to draw the graphs and after that, we are determining the individual generations. How many of you have understood? I'm ready to do another problem. How many of you can do a problem now? How many of you can draw the graph?
Can you explain again, sir, the graph after plotting those two P1 and P2?
Yes. Yeah. After plotting P1 and P2, now on the x-axis you do have a demand. This is your total generation, which is also your demand also. So this is your demand, isn't it? Demand x-axis में draw जाएगा, P1 and P2 y-axis में draw जाएगा. So first of all, P1 curve this है ना, next P2 curve this है. So this indicates my demand. So let us suppose if I need 170 megawatts of demand, so I can directly draw a line here, and it cuts these two curves at some point. So this is going to be my P1 generation, and this is my generation at second plant P2. So for this demand of 170 megawatts, P1 is this value, P2 is this value. If I go with 325 megawatts, this is 325 megawatts line. This is my P1. This is my P2. Let us suppose 500 megawatts. These curves may cut here somewhere. So this is my P1. This is my P2. If I don't have the curves, it will be easier if I vary the demand. I can easily find out. The only problem lies is calculating all these things and plotting a curve. Now we'll try one more problem now. With constraints. Consider two plants with the characteristics. I will directly give you ICs now. Carefully see the question. Two ICs have been given for you for two different plants, and there is a constraint, if you carefully observe, that the generations cannot be less than 25, and the generations cannot be greater than 250 for each of these plants. So the minimum and the maximum generations of each of these plants is 25 and 250. Now determine ELD without losses when the demand is varying from 50 to 400 megawatts. Now, have you gone through the problem? Now let's get back to the solution. First of all, let's draw the table. We are going to solve this problem with a graphical representation or with a graphical data. So first of all, let's draw the table now. Given IC2 is equal to this one. So I'll take this one as lambda because for ELD without losses, DC1 by dP1 must be equal to DC2 by dP2, which must be a constant value. I'll take it as randomly as lambda. So this is going to be lambda, this is going to be lambda. So in that case, P1 is equal to lambda minus 2 by 0.02. Lambda minus 2 by 0.02. If you want, you can solve this one. So isn't it? This is P1. Next is P2, which is equal to lambda minus 3 by 0.0. This is nothing but 100 lambda minus 300. This is P1, this is P2. Now I'm going to draw a table now again. Lambda, P1, P2, and the total sigma Pi. So first I can again start with 0. I'll again start with 0. So I'm again starting with 0. Can somebody say me what are P1 and P2 values? Both are 0 and 0. So the total generation is 0 again. Now if I keep it as 1, this is going to be again 0. How many of you are following actually? Can you raise your hands so that I can see? So getting back for you again. For ELD without losses, your condition is IC1 is equal to I2, and this is some random value. IC1 is already given for you. So equating to lambda, I will get P1 is equal to lambda minus 2 by 0.02. If I solve this one, I will be getting 50 lambda minus 100. Similarly, these are my equations now. Now I am drawing my table lambda, P1, P2, and the total generation. I'll start with the value of 0. Or you can choose any random value which you want. 0. So if I substitute here, P1 will be minus 100. Generation cannot be negative. So normally in earlier days I have kept it as 0 because generation cannot be negative. But here there is a constraint, if you carefully see, that my generation cannot go beyond 25. My minimum generation must be 25. So I will write it here as 25. If this constraint is not given, we are supposed to mark it as 0. But since there is a constraint that minimum generation must be 25, I am keeping it as 25. 25. And P2 is also, if I keep lambda is 0, P2 will be again 0. It will be 0 minus 300 minus 300. Again, minimum value 25. So my total generation is 50. Now if I keep it as 2, so 1 by 4 together, 1 also you can go. It is a random value. If you want, I'll keep it as 1. Again, you will be getting a negative value, isn't it? Here, what you will be getting? Minus 50. Again, to be rounded. Here, minus 200. Again, to be rounded. 50. Next, 2. It is 0, but it is to be rounded to 25. Here, it is minus 100. Again, to be rounded to 25. Next, 3. This is 50. And this is what is this value? 0. 75. Next 4. This is 100. This is 100. 200. 5. 150. 200. This is 350. 6. This is going to be 200. This is going to be 300. This is going to be 300. But you do have an upper cap also. It states that the maximum generation must be 250 only. So that's why again I am capping it to 250 and making round figure at 450. At 7, 250. This is going to be 400. Again, there will be a capping. And this is my 500. See, check the caps here. Upper generation also cap is there. Lower generation also cap is there. See, my total generation has been reached, and so I will be stopping the block. Now, if I plot the graph, sigma pi, or what you call it as a PD. First of all, P1 with respect to PD. This is on x-axis. This is on y-axis. Up to generation 75. So this is one is going to be P1, the other one is going to be P2. So if I want any generation in between, I have drawn here up to 50 to 100 megawatt. If I want any generation, single generation, say this P75, I'll just draw a straight line, and this is going to be my P1, this is going to be my P. Any intermediate value, I can go with these. I hope you have understood how to go with economic load dispatch without losses using graphical method. Now, when can I employ this method? If my demand is not fixed, and if it is varying over a large scale, then it is better if I go with the graphical method. If my demand is fixed just only to an arbitrary value, to some random value, then better you go with the previous method. Directly use that equation. Those two equations, solve them, you will get the answer. But if the demand is varying like this, indefinitely, Better go with the graphical method of solving. Now, I'm going to a little bit complex problem. I'm considering 3 plants now, which do have the characteristics of I'm assuming that these 3 are the characteristics of 3 plants, and from new generations with ELD without losses for demand of 1000 megawatts. So this is the problem. Now we will go with the first method of solving the problem. What is the first method? We choose 2 equations. Equation number 1 is summation of all generations is equal to demand. So what are the 3 generations now? P1, P2 and P3 is equal to 1000. This is equation number 1. Equation number 2 is all ICs must be constant. How many ICs I do have? I do have 3 ICs. So I'm making all of these things as constant. So what is this one? 0.02 P1 plus 2 is equal to 0.01 P1 P2 plus 3. 0.03 P1 plus. This is my second equation. Solving 1 and 2 will give me an answer. So how to solve this 1 and 2? Equation of P2 I will get P3 also I will get it also. The choice is yours. That is subject is. My train is P3 of this person. I employ these 2 equations. So P1 is equal to 0.03 P3 minus 1 by 0.0. This is my 1.5 P3 minus. Similarly, I employ these 2 equations, and my equation will be so I'll substitute these 2 things in this one. So this is equation number 3, P1 in terms of P3, P2 in terms of P3. Substituting 3 and 4 in this equation. Substituting 3 and 4 in equation 1. So what I'm getting? 1 plus 5.5 P3 minus 250 is equal to 1000. So P3 is equal to 750 by 5.5. Something around 136, I think so. If I get P3, then I can go with P1 and P2. So what is P1? If I substitute P3 value here, I'll get P1. If I substitute P3 value here, I'll get P2. So P1 is equal to. Can somebody do this for me? P1 and P2.
Sir, P3 1250 by 5.5.
ఇది ఎంత అన్న P1 ఎంత
P3 1250 by 5.5.
1250 ఓకే ఫైన్ ఆన్సర్ 1250 by 5.5 సో ఎంత వస్తుంది ఇది సో వాట్ ఇస్ ద వాల్యూ
P1 is 291 megawatts.
291 right P3
P1, sir.
ఇది చేంజ్ చేశారా లేదా
P3 is 227.27, sir.
P3 యా
227.27, sir. P3.
okay very good so what is P1
P1 is 290.90.
okay what is P2 then
2 is 481.81.
So like this, P1 and P2, P3 values. So this is about economic load dispatch. These were the problems which were asked in your competitive exams, GATE, DSC, your IES examinations. ELD without losses. And in the next class, we will see problems, tutorials on ELD with losses. And before going for that, we'll just see what is the difference in the conditions. So once again, a quick review, how to solve this problem. Either you go with the direct method or you go with the graphical method. If the demand is fixed, you go with the direct method. If the demand is just varying, you go with the graphical. In direct method, there are only two conditions. One is sigma generation is equal to demand. Second thing is ICs must be constant. Whereas in graphical method, what you are supposed to choose? Get KI equations, vary lambda, and determine generations and demand. Next, draw the graphs, and from the graphs you determine the individual demand. So 3 steps there, 2 steps here. Which one you want, you can try it. This is about ELD without losses, which is commonly used for your competitive examination. This is commonly asked for your competitive examinations. But sometimes they are asking this ELD with losses also. I'll just give a glimpse now. In the next class, we will see the derivation along with the tutorial. Tutorial on ELD with losses. So how to include the losses now? In the earlier column, what we have done, our aim or objective, whatever you say, it is minimization of total cost, isn't it? This is equal to your target is minimize total cost of generation, which is summation of all the generations at all the plants. Like CI that represents the cost of generation at I plant, and CI is a function of P. So summation of all the costs is to be minimized. Now your target is minimization of C at all the plants, subjected to Earlier case, what we have written, the total generations must be equal to your demand, isn't it? The total generations is equal to your demand. But now, since we are considering losses, your equation gets modified to this. Sigma PGI is equal to PD plus PL. Sigma PGI is equal to PD plus PL. So now what is my condition? Minimize CI subjected to sigma PGI is equal to PD plus. So what is my auxiliary function now? Sigma CI is lambda into this is my question. I have just enclosed this constraint into the main problem. This is my main problem. I am supposed to minimize this one with this constraint, and I have added some value of lambda, some arbitrary constant, called as the Lagrange multiplier. So now, for getting minimum value, I am assuming this entire as a function. For getting minimum value of this function, what I am supposed to do? I am supposed to go with first derivative of this entire function. Demand is considered as a constant one, which is independent of the generation. Demand is independent of the generation, and so it is considered as a constant one. As far as loss is not a constant one. Losses vary with the generation. I'll show you how the losses vary with the generation. This is the condition. Earlier, what we have got the condition lambda is equal to dci by dpci. Only this was the condition for us without losses. But now what we have got another term in the denominator, which is 1 minus dpl by dp. That we will solve tomorrow. So that's it for today. So what we have learned today, we have dealt with graphical method of solving the ELD problem without losses. And we have taken up a small introduction on ELD with losses, where we have seen that a new term will come into picture now, which includes the losses. When we are solving this problem of ELD with losses.